deemed approved. Tonight we are delighted to have as our speaker Robert Ehrlich, Professor of Physics at George Mason University. Dr. Ehrlich earned a BS in Physics from Brooklyn College and a PhD in Experimental Particle Physics from Columbia University. While he was at Columbia, he worked on the Nobel Prize-winning two-neutrino experiment. Recently, he has focused on energy production and use, particularly renewable energy, and has started a renewable energy undergraduate major at George Mason. Tonight, we are pleased to welcome him and to learn about why the debate over climate change has become increasingly polarized. He will tell us about various renewable energy technologies, and in particular will inform us about the latest research on modular nuclear reactors. He will then reframe the debate using the concept of clean energy rather than renewable energy. And he will argue that clean energy will be the most defensible and affordable way for us to meet our energy needs in the future. Barbara.
The original title for this talk was Renewable Energy versus Climate Change. And I have to thank Larry Milstein for suggesting this very clever alternative, which I think captures the two themes of what I want to talk about tonight. And that is, I believe that the primary focus of our attention should not be on climate change, but on energy change. Certainly, concerns about climate may be a factor in driving that change, but as I say, for various reasons, not just political, but various reasons, I think that the main focus should be on energy change. Also, I think we want to broaden the debate to consider clean versus green. Now, you're probably aware that clean happens to include nuclear, and this is not the greatest time to make a pitch for nuclear, but I'm going to forge ahead anyway. And let's see, this should advance it? No.
Page down.
Page down, okay. All right, and I suspect that the usual tradition is to have questions at the end anyway, but just in case that wasn't the case, I thought I'd mention this. I'm sure a few of the things I may say you may disagree with, but if you would please hold questions and comments. Oops, I was wrong direction. Okay, just to start with the climate situation. I'm sure everyone has seen this graph of surface temperatures over time, over the last 150 years or so, and there does seem to be an increase in recent decades. In fact, the change is roughly 0.2 of a degree per decade. Let me just briefly summarize what this august body, the IPCC, maintains about this. There is, projecting forward over the course of the next century, believed to be an increase somewhere in this range. I would call your attention to the rather large size of that range. The size of the range primarily has to do with uncertainties over how much greenhouse gases are going to be put into the atmosphere, but also uncertainties in the models, excuse me. There's also the fact that it's projected that the warming will be very unevenly distributed around the globe. And then the final point I wanted to make here is that according to most climate scientists, we can't stop climate change. even if we take drastic actions, we could only mitigate it. In fact, I find it rather interesting that even if we were to reduce emissions of greenhouse gases to zero starting now, there still would be built in to the system this kind of increase over the course of the next century due to the inertia in the system. Now, if you were to take this range up here and subtract the average increase projected with no new emissions, what you wind up with is this, that the projected increase over the course of the next century is believed to be somewhere in this range, 0.5 to 5.8 degrees Celsius for Fahrenheit increases. You would, of course, roughly double it. I find that an astoundingly large range of projections. Okay, anyway, so much for what the claim of the IPCC is about the global climate system. One topic I would like to address is this increasing partisan divide in views on global warming. And it really is striking. If you go back, let's say, to 1998, there was hardly a difference at that time between the views of people according to their political affiliation. And the latest data from 2009 shows a 3-to-1 ratio in views, in skeptical views, based on party affiliation. Now, it's not entirely clear that this difference reflects views on global warming itself. It could be more views on the media. But in any case, I find it striking that this chasm based on one's politics has in fact developed. Now, for those of us who are in academia, I think it's probably fair to say that most academic scientists are very sympathetic to the views that human-caused global warming is a proven reality. This is a lament that I suspect most academic scientists would agree with. It is true, I believe, that unfortunately the US public is not very scientifically literate, but nevertheless, to make the leap from that to say, well, if only they knew more science, surely they'd understand that global warming is a dire threat. However, there's a very interesting study on this matter, and this is basically what it summarizes, and that is that among survey respondents who were better informed about global warming, they both feel less personally responsible for it and also show less concern about it. I find that an extremely interesting finding. I'm not exactly sure what to infer from that, but it has been called the global warming paradox, incidentally. Okay, so let me briefly address this question of why the increasing polarization. I think the reasons can be put into three categories. First of all, is the nature of the problem itself. Whatever your views on global warming, it clearly is a very long-term problem. It's foolish to attribute a warm winter or a cold summer or whatever to global warming, because we're talking about a problem, if it is real, that is going to occur over the course of a very long period of time. Also, and therefore, if it is a very long-term problem, clearly one's views on the matter really depend very much on long-term thinking and how you weigh the needs of the present, getting out of, say, our economic doldrums versus the needs of people 100 years downstream, if indeed humans are still around as we know that now. There are folks, by the way, who claim that there's going to be this singularity in 2045, and so there's no point worrying about stuff beyond that. Also, it's a problem not only that's very long-term, but the magnitudes of the actions needed to mitigate it, and all we can do is mitigate it. It's going to occur if it's going to occur. But the actions needed to mitigate it are really rather drastic in terms of changing the way we use energy and other resources. So there's that. There's also the nature of human beings. Unfortunately, I guess this attitude, my buddy is right or wrong, is just a fact of life. I asked one of my colleagues in another science department what was his strongest argument for being skeptical of global warming, and he said, well, the Democrats are for it. I think he was joking, but he has a similar sense of humor to mine, so I suspect he was. It's also true that in a matter where there are uncertainties and where you may not be 100% sure of your position, sometimes there's a tendency to kind of dig in when your position is under attack. And there's a very interesting article, When in Doubt, Shout, that gets this idea across. So nature of the problem, nature of the human beings. There's also the nature of the science behind the problem, and that is we're mainly talking about computer models here as against doing an experiment and getting an experimental result. Moreover, the computer models are such that, in a sense, you know what the answer is that you're trying to get. I'm not saying there's any fudging that goes on here, but that is a danger if you know the answer ahead of time. Then there's the matter of the very large uncertainties. I've already alluded to that one. There's also the fact that different aspects of the problem have very different levels of uncertainty. So, for example, I think there's no doubt whatsoever that humans are contributing, probably to a significant degree, to warming. However, when people start talking about a so-called tipping point where the climate system is sent into a whole new regime that's unrecoverable, and claiming to know that the tipping point is 2 degrees Celsius, I think that's an example of something that is really quite extremely uncertain. And my favorite way of putting it is that there's lots of irrelevant facts on both sides of the argument. Let me give you some examples of irrelevant facts on each side of the argument. By the way, what do I mean by irrelevant facts? Well, they're facts, they're true, but the conclusion drawn from them is not correct. So here are a few. People who are very skeptical about global warming will point to the large ancient swings in climate that occurred before humans. So why do we blame humans now when these large swings occurred before we were around? Well, it's true that there were these large swings, but so what? It doesn't mean that there can't be another cause today that's operating in addition to nature itself. Here's another one. Water vapor is the most important greenhouse gas, so why worry about CO2? Well, I won't tell you why that's irrelevant. I hope you know the answer to that. In fact, I think I'll just go through one or two of these others. Here's another one. No clear change in global temperature in the last 5 or 10 years. Well, of course, if you look at a relatively short period, like 5 or 10 years, you're not going to see a clear trend because there's lots of noise in the data. And so you really have to look at a longer period than that to see the clear change. Or temperature rise by 2100 could be beneficial. Well, actually, that's true. If the temperature rise is at the lower end projected by the IPCC, it could well be beneficial. But that's not relevant. Okay, just to show you that I'm not entirely biased, here are some irrelevant facts on the other side of the argument. Ancient global warming was strongly correlated with greenhouse gas levels. Some supporters of global warming make this point to show that, of course, greenhouse gases are a significant factor in climate change. But who knows which direction the causation was in? In fact, the evidence is that it probably was the warming that caused the greenhouse gas levels to rise rather than the reverse. Or this one. Without drastic action, rise in temperature may exceed this 2-degree Celsius tipping point. Well, I think I already mentioned that. The key point here is that we're saying may here or could. Well, sure, who knows where a tipping point is, if one exists at all. It could happen, I don't know. But is it really relevant if you don't know that there's a tipping point and where it is? Or this one. Global warming is likely to be associated with an increase in extreme events like severe storms, floods, droughts, and so on. Well, that's actually true. It's likely to be, but it's not relevant when people extend this to deal with the situation that's happening in the world today, as many people are wont to do. For example, I've seen this graph, before I mention that, the extreme events is given the more poetic name global weirding. I think one of my favorite columnists, Tom Friedman, used this in an article he wrote about the problem. And this is supposedly evidence for global weirding or the rise in extreme events. This is a plot of the number of severe storms in the North Atlantic versus time. When I first saw this graph, I said, my God, this is clear evidence that there's something really wrong going on now. But then, after looking at it a little bit more, I found 4 or 5 reasons to suspect that this graph was completely bogus. What are the 4 or 5 reasons? First reason, you'll notice the graph doesn't start at 0, it starts at 8. There's a number of storms versus time. Starts at 8. Obviously, 0 is way down here. Okay? So obviously, that's going to exaggerate the increase, the fact that you suppress the 0. Second, the choice of the start date is completely arbitrary. So if you want to make the point, you're going to start at a date before there's a drop from earlier, an earlier high level. Third point, what's plotted here is not the actual number of severe storms, but the 5-year moving average. Doing it that way makes the data look much smoother, smooths out all the more radical ups and downs, and therefore makes this appear much more pronounced. What am I up to now, 3 or 4? Whatever. Next reason, and most important of all, this data, oops, wrong direction, sorry. This data is primarily bogus, not only for the 4 reasons I already mentioned, but for the fact that this entire increase can be explained on the basis of NASA being able to detect very short-term storms, which they previously were unable to detect. And this shows it very nicely. The short-duration storms show a pronounced increase as detection methods improve. So if you take all those things into account, as I say, this kind of graph is completely bogus. But what is the lesson here? The lesson here is be very careful with statistics and graphs that look too impressive, especially if they fit your preconceptions, okay? You can really fall into a trap if you want to believe something. Okay, so let me now make the transition to energy. And I think while there is this big political divide on the question of climate change, the divide is much less when it comes to renewable energy. So what's shown here is public support in the US for renewable energy conservation, improved efficiency, and so on. And while there still is something of a divide, it's not nearly as great, and there is generally broad support among both Democrats and Republicans for renewable energy and conservation. Now, I said before, I think the main focus should be on energy rather than climate change. And my reason for saying that is because I believe the arguments in favor of an energy change go way beyond any concerns you may have about climate change. The environment is, of course, a significant factor still, but not just climate change. There's many other environmental consequences associated with using our dependence on fossil fuels that go well beyond climate change. The BP disaster, the fatalities associated with mining coal and so forth, and other damages to the environment from fossil fuels, all need to be considered. Then there's the economy, together with national security. So, for example, you may have seen plots like this, which show both the domestic production of oil in the US, and on the same graph, imports. And of course, the imports continue to rise, production falls. And so despite the pledges or assertions of just about every past president since, Jimmy Carter, about the need to become more energy independent, the trend over the years has steadily, increasingly been in the reverse direction. This clearly is bad for the economy. It's also very bad for national security. Witness what's happening now in Libya. It's not just Libya, of course, that people are worried about, but the whole Mideast region. So clearly, we'd be better off if we could get off our oil addiction. It's also global security. I mean, wars can get started over competition for resources, especially energy. Not just global security, but global competitiveness. This I meant to show this slide before when I was talking about a slightly different subject. This is a graph basically illustrative of what's called the peak oil phenomena. The idea of peak oil has been around a long time, I believe since the mid-50s, first suggested by Hubbard. The idea is that at some point we're going to reach peak production, and from then on, the amount of oil produced is going to steadily decline. And there's reasonable evidence to suggest that we may be at the peak just about now. Well, if that's the case, then we really don't have a choice about switching away from fossil fuels, particularly oil, which is used entirely for the transportation sector. It's going to be forced upon us, but the transition is going to become increasingly painful because as the produced oil declines, I mean, there is a finite amount of the stuff, as it declines, competition for it is going to increase, and the price of it is going to continually increase, since it's become increasingly scarce. On the competitive matter, we often compare ourselves to the number 2 economy in the world, China. There's this slightly strange phrase that President Obama has used about who's going to win the future. I learned recently, however, it's not just an Obama phrase. Newt Gingrich used the same phrase. So it's a bipartisan phrase. But I think that really is an issue, whether the U.S. is going to basically stagnate in terms of new technology in the future, or whether it's going to be a leader. As far as renewable energy is concerned, we used to be the leader. Now China has overtaken us in terms of investing in it by almost a factor of 2. We combined are the number 1 and number 2, as I already said, not only in terms of overall economy, but also in terms of renewable energy. But look at the difference in the growth rates in the 2 countries in renewable energy. And the Chinese have also adopted what's called a renewable energy standard, setting aside a certain fraction of energy to be gotten from renewables over time. Secretary Chu, Secretary of Energy, has made this statement, which I think is probably true, that what the U.S. and China do over the next decade, particularly as far as energy is concerned, will determine the fate of the world. Okay, first, a few characteristics about renewable energy. As you know, the fuel is free. The sun shines, and we don't have to pay for it. The wind blows, and so forth. It's also inexhaustible. Well, okay, the sun is going to last maybe another 4.5 billion years or so, but that's pretty inexhaustible. In contrast to many other forms of energy, it is extremely capital intensive. That is, the fuel is free, but you have a big upfront cost. It is also environmentally benign. I have to say relatively, because just about any technology will have deleterious consequences, as I'm sure you know. Examples include biomass, hydro, wind, solar, geothermal, tidal, and wave energy. The main ones that have been developed so far, nearly 90% of the total are those 2. That's true both in the US and worldwide. But the fastest growing is actually wind, both in the US and worldwide. Wind is currently, among the various forms of renewable energy, probably one of the most cost competitive. The cost per kilowatt hour has been steadily coming down, and the amount installed has been rising at a quasi-exponential rate. There are challenges associated with renewable energy, and these are a few of them. As I already alluded to, the cost is not quite there in many cases compared to traditional energy. It's extremely variable in some cases. The wind doesn't always blow at a constant rate, the sun doesn't always shine, and so forth. It tends not to be near population centers, which poses a problem for the electrical grid. And then finally, it is relatively diffuse, which means basically you require a large footprint to harness a large amount of energy. However, on the question of the large footprint, Let me just remind you, that turtle whirling in is just a reminder that a large solar project scheduled for the California desert using solar thermal electric was apparently put on hold as a result of concerns for the desert turtle. But anyway, to give you some idea of how large a footprint is required, oh, and isn't that nice? This is Libya over here. But this is a map of the Sahara Desert. This is the kind of area you'd need to supply all the world's electricity, okay, with solar power. So even though it is relatively diffuse, we're not talking about covering the planet with solar cells, not by any means. And apart from the desert turtle, the kinds of areas that you'd put solar collectors in are often not used for agriculture or population or whatever. I did talk about cost before. This is a comparative cost per megawatt hour of various renewable and non-renewable forms of energy. You'll notice some of the renewables definitely are at the bottom here in terms of comparative cost. Coal and natural gas still are the two cheapest forms of energy. This is data from the U.S. Department of Energy projecting forward to the year 2016. But there are a couple of renewables up here that are quite close to coal and natural gas. Moreover, for renewables, the projections keep getting better in terms of cost per kilowatt hour. I mean, obviously, as more and more is deployed, the economies of scale will lower the unit cost, and as research continues on making solar and other forms more efficient, that will also lower the unit cost. And so it is projected to continue to decline in cost. This is photovoltaic cells. So right now, this is 2010 or 2011, we see that there actually is a state of the union where the cost of solar on your roof is actually equal to the cost of electricity from the grid. But that won't be the case for the U.S. as a whole, or on average, until 2020. But still, that's very encouraging that projecting forward over the next decade, this will be the case, hopefully. With regard to the question of the variability of solar, wind, and some of the other renewable energy forms, I have to point out this is already a problem even apart from renewable energy because of the varying load imposed on the electric grid. And we've managed to deal with that. Of course, it will be more of a problem as more renewable energy is added. Furthermore, the variability is really not an issue at all with some of the renewables, particularly hydro and geothermal. But whether we have more renewable or not, we clearly, I think, do need a smart grid to basically match supply and demand. A smart grid would, by definition, do that. And then also, renewables call for a greater energy storage capacity. So those are some of the challenges, some of which are already being dealt with. Now, there are people who believe that by the year 2030, that if we really set our minds to it, we can have 100% of our energy from renewables. I'm not sure that that's the case. I think that requires some very optimistic assumptions. And my suspicion is that it could be a fairly costly undertaking if we choose to go down that road. I'd like to now talk about some specific renewable technologies that I think are worth taking a look at before getting to the controversial nuclear question. First, I mentioned before that renewable energy, particularly solar, is quite variable. This is one form of harnessing solar energy that gets around that problem in a very interesting way. What you have here is a large number of mirrors that concentrate the sunlight on the top of this tower, allowing you to reach temperatures on the order of 700 degrees Celsius, hot enough to melt the salt that is in the tower. And the salt is pumped into a large storage vat underground. And it's so hot, and you have so much of it that it can't really lose its heat overnight, that you can actually use the molten salt to power a turbine that generates electricity night and day on a continuous basis. So that's kind of an interesting way, excuse me, an interesting way to get around the problem of energy storage and variability. Well, everybody knows about solar and wind. I thought it would be interesting to mention three technologies that I consider, quote, underappreciated. You can judge for yourself whether they're underappreciated, but, and I'll say why I think they're underappreciated too. The first one is the so-called solar chimney. And the way this thing works is it harnesses solar in a rather unusual way. That is, you have a very tall chimney shown here, and this blue line is actually a large layer of a transparent material, either glass or plastic or whatever, that allows the sunlight to pass through it. And then you have a dark layer of material underneath it that gets heated by the sun, and the heat is kind of trapped underneath this, this piece of plastic. And as a result, since hot air rises, the air basically goes up the chimney, and that, of course, sucks in air from all around. And so you basically have a continual updraft of air. And if you then put some wind turbines in the chimney here, you can basically harness the rapidly moving air. In fact, it actually works day and night because the heat is basically trapped underneath the collector at night, and it still rises up the chimney. This idea has been around quite some time. A prototype was built by the Germans in Spain in the early 80s. The chimney height was close to 200 meters, with a diameter of the collector here, 244 meters. There were some problems. One major problem is that the amount of power produced, given the size of the thing, was not very impressive. Only 50 kilowatts, and the efficiency was actually much less than 1%, which sounds like a killer right there. But it was very cheap to operate, at least until the chimney collapsed. Anyway, not to be discouraged, there is an Australian company that's looking for somebody to give them the money needed to build a vastly larger facility, something that would generate 200 megawatts, considerably larger. In fact, the design for this thing the Empire State Building, by the way. So we're talking about something that's roughly a kilometer high. Yeah, that's the Eiffel Tower and so on. Why does it have to be so big? Well, this is why. You can show, using a little bit of physics, that the efficiency of the chimney, theoretically, is on the order of g times the acceleration of gravity times the height of the chimney, divided by the specific heat of air times the ambient temperature. By the way, this formula clearly is wrong, which one of my students pointed out to me, because it predicts an infinite efficiency as the height of the tower, the height of the chimney goes to infinity, which is nonsense, okay? So, but it's an approximate formula. But the interesting thing about it is that it scales, the efficiency scales with the height. So the taller you make the chimney, the more efficient it becomes. Now we're used to systems where the amount of energy you get scales with the dimensions. But here the efficiency scales with the dimensions, which means that the amount of energy you get scales with the square of the dimensions, okay? So that's why it's important to build a really large structure. Anyway, a colleague and I at the university are playing around with this technology. We're not building anything, we're just doing some simulations and using fluid dynamics to see if we can improve the efficiency, because given the low efficiency I mentioned before, improving efficiency could go a long way, aside from increasing size. Oh, and the other thing is that according to people that have looked at this, they happen to be proponents, but that's the way it is, they claim a rather impressively low cost of electricity for such a device. I guess that will encourage investments. Okay, the second underappreciated technology I want to talk about briefly is geothermal. Now, the conventional wisdom on geothermal is that it's great for producing electricity where conditions are right. If you're near plate boundaries or places like that where there's a lot of thermal activity, you don't have to go nearly as deep to access the high temperatures you need to generate electricity. But the places, particularly in this country, where that is achievable are few and far between, mainly out west in certain places there. That's the conventional wisdom on geothermal. As I'll explain, I think it may be wrong. This is a graph that shows the cost of drilling geothermal wells. And by the way, if you do want to access very high temperatures for geothermal to produce electricity, and you want to do it in an unfavorable place, you really got to go very deep, like 5 or 10 kilometers deep. And that's very, very expensive. How expensive? Well, studies on the cost of drilling wells, which interestingly is proprietary data because the oil companies don't like to share the data, but still, the data does exist. The data, and I say oil wells rather than geothermal wells because there's much more data on drilling oil wells. But it shows that based on conventional drilling methods, there's actually an exponential increase in cost of drilling the well with depth, okay? And by the way, for geothermal, the main cost of the system is drilling the well. That's the main cost. And it's hard to beat an exponential, all right? If you want to go down to 10 kilometers, which is out here, well, the exponential is way through the ceiling, okay? Why is it, incidentally, that it's exponential? I think there's a simple reason. Because any function where going the last delta z gets increasingly harder by a fixed percentage, that's going to be an exponential function, okay? In fact, I beg your pardon, it's proportional to z. Going 1 more kilometer after you've already gone z kilometers is proportional to z. Why? Well, because the bit gets stuck, you have to pull the bit up to change it all the way, and so forth, okay? However, there's a new method of drilling deep wells using something called spallation, and the people that have come up with this method predict a linear increase in cost with depth. Well, that makes all the difference in the world. Why does it make all the difference in the world? Well, because the available resource as you go deeper is not linear. The available resource increases something like that. It's faster than a quadratic. It starts out at 0, 0 being the minimum depth to reach hot enough temperatures to create electricity. And it increases very rapidly. So therefore, the deeper you go, the more resource you get per dollar, if this is really true, if this is a linear increase in cost. So that would be very exciting if it is true. I say if it is true because so far it's just been tested in the lab. They haven't really tried it in a deep well. So what is this spallation drilling? Looks like this. Basically, you don't have a drill bit at all. Instead, you have a fuel coming out of a jet, with a flame produced by that, and that hot flame against the rock causes little pieces of rock to flake off. The pieces are small enough so that this whole thing, which by the way is underwater or drilling mud, can be flushed out continuously. You never have to change bits. You never have to haul up debris because the debris is brought up continuously. Anyway, that's the idea. Again, it's been tried in the lab, but it's not been tried for wells, particularly really deep wells. So we don't know if it's really, really true that the cost is linear with depth. But if it is, my claim is that that makes all the difference in the world in terms of the availability and cost of geothermal for electricity. By the way, for other uses like heating, geothermal is fine just about anywhere. Okay, the third technology which I claim is underappreciated is something called dynamic tidal power. Tidal power has the same rap as geothermal, namely it's great where the conditions are right, but there's very few places in the world where it's right, like the Bay of Fundy or places like that, where the natural tides are very high and you can harness them to produce electricity. How do you harness them? You create a dam in some estuary, and then as the tide goes in and out, you develop this height differential across the dam. That height differential drives a turbine. In fact, it drives a turbine whichever side is the higher one. And then you create electricity from the turbine. As I say, there's only a few places in the world where the tide is high enough to get an appreciable, they call this difference in height, they call it a head, to get an appreciable head to give you power. But a little over a decade ago, a couple of folks in the Netherlands came up with this idea of what they call dynamic tidal power. How does that differ from the conventional tidal power? By the way, can somebody tell me when I have about 5 or 10 minutes to go? Okay, thank you. In dynamic tidal power, you don't build a dam across an estuary. Instead, you go someplace off the coast of some country and build the dam straight out to sea. Seems kind of crazy because you're not enclosing anything. But you build this dam straight out to sea. And we're talking about a really long dam, by the way. The folks who came up with this idea suggest a 60-kilometer dam. Can you imagine such a thing? But anyway, why? First of all, what's going on here? Well, based on both calculations and actual observations, you can show that by doing that and interfering with the tidal current flowing along the coast, you create a head across the dam. In fact, the further out you go, the greater the distance d, the greater the head. So if you go out, let's say, 60 kilometers, you get a significant head, maybe 2 or 3 meters. Whereas if you only go out 1 kilometer from the coast, you get a very tiny head. And therefore, this is another one of these projects similar to the solar chimney, where you really have to do it on a big scale in order to get anything significant. They make this claim, by the way, that with a 60-kilometer long dam off the coast of China, you could actually generate 30 gigawatts. That's an enormous amount of power. So what do the 3 underappreciated technologies share that I mentioned? Here that they are. Well, none have been tried yet on a large scale. Why? Not because they're necessarily silly, but because only a large-scale project can give you a significant amount of power. You only get a very fiddling amount of power on a small scale. And so you have an obvious chicken and egg problem here. Investors are not going to be willing to invest in something that's unproven. And it is a big upfront investment for any of these things. Okay, now let me transition to the other part of my talk, namely that I'm advocating for clean versus green, or renewable. So clean includes natural gas being cleaner than coal and petroleum. It also includes nuclear. I realize this is not the greatest time to be making a pitch for nuclear, but here we go. We are well aware what's happening in Japan these days, and you really have to admire the character of the Japanese people. But to put things in perspective, it's always risky, incidentally, when talking about something that's unfolding as we speak, to say just how bad it's going to be. But I believe most people who've looked at it carefully are of the opinion that it's not going to be anything close to Chernobyl. And that's not a sure thing, but that's the general opinion. So, okay, let's take Chernobyl, the worst nuclear accident in history. Chernobyl exposed residents in the highest exposed areas of the Ukraine and Belarus, 5 million people, to this level of exposure over the course of the 20-year period indicated here. That's how much radiation they got. By the way, as far as worldwide exposure is concerned, averaging over the globe, we're talking about a considerably lower number. How does that compare with the radiation we receive from all around us every day? Well, the natural background varies quite a bit from place to place on Earth. This is a typical range, although there are some higher and lower. The average is about 48. Notice that this is particularly people living in these areas, the 200, significantly higher than what the people in the most exposed areas of Ukraine and Belarus were exposed to. And we're talking about the same kinds of radiation. Radiation from nuclear reactors and from natural radiation. It's not two different kinds of radiation, same kind of radiation. And also incidentally, there's been no indication that people living in places where the natural background is very much higher or lower suffer any different cancer rates. Actually, there are some studies that indicate people in higher radiation areas have less cancer, at least. There's been one very controversial but not necessarily wrong study by Bernard Cohn at the University of Pittsburgh claiming precisely that if you live in a county with high radon levels, your chances of getting lung cancer are less. But anyway, I think it is instructive to compare the kinds of radiation exposure due to Chernobyl, even in the most exposed areas, with what we receive every day from background, and we get much more from background. And there's no studies whatsoever that indicate any kind of danger to people living in the higher background areas. So that's something to keep in mind. Moreover, let's make a brief comparison between nuclear and coal, both forms of energy. The World Health Organization estimates that there are about 1 million deaths per year due to coal pollution. Or if you put it in terms of deaths per terawatt hour of electricity generated, you get this kind of number here. What's the corresponding figure for nuclear? Put in Chernobyl, put in the 2,000 or 3,000 cancer deaths predicted over the next, over the lifetime of people, and this is the number you get, a far smaller number. So I think that's another thing to keep in mind. I'm not saying radiation is good for you, although actually there are people who claim that, at least at low levels. But we do have to keep these numbers in perspective. On natural gas, I went to a talk by T. Boone Pickens, who, this is pretty much a quote of what he said, and I think he's absolutely right on the money. If America doesn't kick its addiction to foreign oil by using the natural gas reserves it has in great abundance, it will be seen by future historians as the dumbest civilization in history. It's not that big a deal to convert vehicles to compressed natural gas. In fact, natural gas emits 30% less CO2, 97% less carbon monoxide, and it's roughly half the cost of gasoline, and we have lots of it. Okay, so reasons to promote clean rather than just renewable. Well, as I indicated, it's not entirely clear that we really can go 100% renewable by 2030 or 2050, as some people have claimed. Maybe we can, but whether it's economically reasonable or not is another matter. There's the intermittency and cost issues. As I already said, the U.S. has an abundant supply of natural gas. And then, as I made the argument before, climate is not really our only concern here, or our only reason for energy change. There's many, many reasons to transition away from our dependence on fossil fuels. And I do believe that nuclear is viable, despite the present unfortunate situation, especially small nuclear, and that's the case I want to make. We bypass that one. Okay, small modular reactors, or as I affectionately call them, mini nukes. This has been supported by the administration. It's also been supported by many Republicans. Will these proposals go forward? I don't know. In the present climate, it's, your guess is as good as mine. But here are some of the advantages of small modular reactors. First of all, they're intrinsically much safer than large-scale reactors because they rely on what's called passive safety systems. where it's not a matter of operator intervention, it's not a matter of some generator coming online or something. The laws of physics basically dictate what's going to happen. And therefore, I'm not saying accidents are impossible, but I believe they're much less susceptible to accidents. I'll give some examples of passive safety systems in a few minutes. Also, they're scalable. So you don't have to build a very large-scale plant guessing how much demand is going to be and then find that it's uneconomical when the demand doesn't materialize. But you can basically add them as needed. And so that's very important. They're extremely simple in terms of operations. In fact, some of them have next to no moving parts, as I'll show you. As far as refueling, with many of them, you basically have them fueled at the factory, and then when they reach the end of a, say, 8 or 10 year period, something like that, you don't have to take them down and take them offline to do refueling. You just ship them back to the factory, put them in the back of a truck. It allows you to be grid independent. And this is not just good for security, it's also political advantages. I mean, if you want to serve a small remote community which believes that this is a good thing, you don't have the kind of barriers that you would if you're putting them, let's say, on Long Island or something like that. You can kind of think of these things as, quote, nuclear batteries that can back up renewable energy. Speaking of nuclear batteries, this is, by the way, it's not a joke in the sense that it actually was proposed by Ford, I think before the Edsel. But please don't think I'm advocating for this, okay? I'm not. It's a stupid idea. But they actually were thinking of nuclear battery cars, powered cars. One interesting thing is you'd never have to fill up. Instead of a range of some 300 miles, as with gasoline, or a range of maybe 50 miles with an electric car powered battery. An electric battery powered car, these things would have a range maybe 100 million miles. Is that right? I calculated, I forgot what the number is, but it's well over 1 million miles. In the sense that the one big advantage of nuclear that you always have to keep in mind is the energy density in the fuel is so great, it's like 100,000 times more than chemical fuels, that the amount of fuel you need to supply a given amount of energy is 100,000 times less. So if you literally filled your tank with nuclear fuel, it would go well over 1 million miles. I don't remember what the number is, but well over. The economics of nuclear power is said to be its biggest negative. Well, some people might disagree, particularly in light of the Japanese situation. But it's a very significant factor. Mini nukes get around that problem. And let me explain how. With nuclear, as with renewable energy, the biggest cost is the upfront cost of building a reactor. That's because, well, one reason that's so is the cost of fuel is negligible on a per kilowatt hour generated basis. But with these mini nukes, you get around most of those costs. First of all, you don't need a very large capital outlay. I'll talk about what these things cost more precisely in a little bit, but we're not talking about a cost in the billions of dollars, nothing like that. And with large-scale reactors, it's, of course, people get other people to put up the money for the initial investment. And they're going to want interest rates that are above the traditional interest rate because it's considered a risky investment. And so not only do you have the large initial outlay, but you got to borrow money at higher than normal interest rates. And also, the length of the construction period tends to be rather long for these things. Anyway, with the mini nukes, you get around all this stuff. You just go out and buy, let's say a community of 100,000 people wants a mini nuke to supply their electricity. Well, they just go and buy one. Everybody kicks in a couple $1,000s. There's additional economic advantages. I already mentioned this one, that if you have modular reactors, you keep your options open as to how many you're going to need. You just buy them as needed. The construction costs are much cheaper than with an on-site construction because they're built at the factory, eventually, perhaps using assembly line and standardized design methods as against the one-of-a-kind operation that traditional nuclear power has involved. They can be located very close to the need, not far away, so smaller transmission costs. Given the simplicity of operation, these things have very low maintenance costs. They have no downtime for refueling because basically you send it back to the factory on a truck when you're ready to refuel. So there's lots and lots of economic advantages. Let me just consider a few examples. One of the companies building these is Hyperion. Their design is 25 megawatts. That's enough to power 20,000 homes. And given the cost estimated by Hyperion, each homeowner would have to kick in $2,300 to buy the thing. And for that, you get basically endless electricity. Well, not quite endless. You have to have the thing refueled at the factory, but that's a lot cheaper than buying the reactor. I don't mean to sound perhaps quite as rosy as I've portrayed it so far, because if you think back to the beginnings of nuclear power, people were making all kinds of predictions about it being too cheap to monitor and all that kind of nonsense. And it's quite possible, or maybe even likely, that the eventual costs of these things will be worse than the companies that are trying to sell them are claiming. But anyway, this is a drawing of the Hyperion reactor. It's just buried underground. And it is environmentally relatively friendly. You can call it reactor friendly. Well, that's not exactly how the situation is supposed to look. I'll come back to it. But in terms of scale, the thing is about the size of a hot tub. Here's a person. As I already said, it has very few moving parts. This particular design is not water-cooled, as most reactors are, but it's liquid metal-cooled. Supposedly, it cannot melt down, a big fear that people have about reactors. Why not? Because the amount of fuel is apparently not enough to get hot enough to melt down. The company is now taking orders, incidentally, most of which are in Eastern Europe, but not in the US, of course. It has not yet been approved by the NRC. In fact, I don't believe they've already submitted their application for approval. Also, the system is not quite as compact as I showed in the previous slide. Here's the reactor vault right here. There's a whole lot of extra stuff needed to actually generate electricity, which is done in the conventional way. You take the heat from the reactor, produce boiling water to create steam, et cetera, et cetera. So you really need this whole superstructure, but that's above ground, and the reactor is below ground. But supposedly, the reactor is just buried, put there, left there for 8 to 10 years, and then dug up and shipped back to the factory. That's the plan. Another thing about nuclear is I think a case can be made that it actually is a form of renewable energy. That may seem kind of weird, but the cost of nuclear fuel, at least on a per kilowatt hour basis, is exceedingly cheap. A very small fraction of the cost of the electricity it generates. So it's not quite free like sunshine or wind, but it's extremely cheap. That's one of the characteristics of being renewable. Also, I believe the environmental issues are very much less than for conventional nuclear, certainly much less than coal. So that's another characteristic of renewable. And then there's this one. The fuel supply, I believe, is virtually unlimited. How can I say that? Well, using ocean extraction techniques that have been pioneered by the Japanese, it is, of course, more costly to extract uranium from seawater, but it is present in very low concentrations. And even if it's twice as expensive to get the uranium in the seawater, well, you're just talking about 1.4 cents per kilowatt hour instead of 0.7 cents. So what? So that would be, and given the amount of uranium in the world's oceans, it would be virtually unlimited. So it shares all these three characteristics with renewable energy. By the way, one of the issues that people are very worried about is waste disposal. This, I believe, also has a solution. If before you dispose of the waste, you first extract the transuranic or actinide elements, then the waste will decay to levels of the original uranium ore far quicker than it would otherwise. And so we're not talking about a 10,000-year problem, we're talking about a 500-year problem. I believe the Swedes are, I guess I'm lucky when I made this slide that the disaster didn't happen in Sweden rather than Japan. But the Swedes, I believe, are a model for waste, nuclear waste disposal, as are some other countries. Okay. I did want to say a few things about this. On the other hand, since I think I am at about the end of my time, am I? 3 or 4 minutes. I think I'd rather take questions. If anybody wants to ask me about this topic, I'd be happy to talk about that. But if you want to ask me about some of the things I've said, I'd be happy to do that too. Let's see. Okay, let me start.
And since it is a little hard to hear in this room, if you would stand when you're asking your question, and please try and speak up.
Okay, I don't remember who had the hand up first. Let me take this gentleman.
It's the solar chimneys. Rather than make the expensive and fragile, big, giant, freestanding chimneys. I live in south central Montana, and there's places like by Red Lodge where you could lay a pipe or something like that up to 6,000 feet up the side of a mountain east of Level, Wyoming. It goes up 6,000 to 7,000 feet. And could you just tie a big pipe or maybe a bunch of big pipes together and use them as a chimney and tack them to the side of the mountain, and then maybe even incorporate it with a hot springs of some type to make more heat rather than going up in steam?
Yeah, there are people that have suggested that kind of thing. Another very interesting suggestion, which is patented, is to, rather than, and constructing the chimney is perhaps the biggest construction cost. Another suggestion is to have a floating chimney. You actually make the chimney out of fabric, and how does it get erect? Well, rather than use a sky hook, I guess you may need a sky hook initially in the form of a balloon or something, but once the thing gets going, the updraft itself maintains the thing in the erect position, which I think is a very creative solution, especially if you're talking about a multi-kilometer high chimney. Yes?
Having built one of these, I can tell you why that device is not going to be acceptable. It'll work.
One of which?
One of those chimney generators.
Oh, yes.
As the air flows in from the bottom, it absorbs heat.
Yes.
It starts to move up the pipe. It starts to move up faster until it's flowing over the heat source too fast for heat transfer to efficiently take place. The flow slows down. Heat transfer starts becoming more efficient, it speeds up. You have a standing wave in the pipe, and this thing is going to roar with a sound that will shake buildings miles away.
I imagine it would have to be placed in a rather remote location, but I'm sure there are lots of deserts that are far away from population centers. People will obviously complain about noise, as example, with wind turbines and so on. What was the scale of the thing you built, by the way?
6 feet tall, and I had managed to annoy the inhabitants of every high school in Montgomery County.
My suspicion is that, let's see, what did you make the chimney out of?
Pipe, a metal pipe.
Okay, I can see that you get a lot more noise than if you made it out of, let's say, concrete
It's not the
or
pipe,
something.
it's the air. It's a standing
air.
wave. It's the same thing.
Yeah, but the air has to get out. I suspect the kind of noise you get might not necessarily be much louder in proportion to the height of the chimney or something like that. If you create a standing wave in the chimney, and the wavelength is infrasonic, then it's only going to annoy the elephants. Yes?
Have you become aware, do you know about a project called Green Freedom?
I don't think I am.
Okay, well, Green Freedom, just quickly summarize, is the inverse of what you're considering in the chimney.
Okay.
In the sense that the idea is to build a large tower, like a cooling tower, and you pump cool water up to the top, spray the water out, and this causes essentially thermal instability, and you get a downdraft rather than an updraft.
Mm-hmm.
And the purveyors, or the people who patented this out of Los Alamos, claimed that they could get more energy out than it required to pump the water up to the top, because this downdraft would spin and throw turbines. You're essentially using the instability of the atmosphere to soak heat out of the ambient atmosphere and turn it into flow. So it's the inverse of that, and it might have different noise characteristics.
Yeah.
But I was just curious if you'd ever heard of it.
No, I never have.
Well, it might be worth looking into.
Yeah.
Except somebody, they do have a patent on it, I think, but I haven't heard much about it in several years.
Interesting. Let's see. Yes.
Is there something in the inherent design of these mini reactors that means that they're not amenable to being scaled up to larger sizes?
With some of them, yes. Some of them very definitely are only work based on being small. In fact, there was one very pretty one that I thought I had that I wanted to show you, the pebble bed reactor. I'm surprised I couldn't. Let's see now, where's my icon? Anybody see an icon on the cursor, I beg your pardon. Where's the cursor? I'm sorry? Oh, okay. I'm used to this type. Well, I'm not going to be able to get it. Okay, never mind. The pebble bed reactors, I think one example that you would very definitely wouldn't want to scale up.
Bottom.
Oh, no, I don't know why it, I must have hidden it or something.
At the bottom.
The bottom?
There you go.
I can't find the slide. Could you get a slide sorted here? We can find it that way. But yes, some of them have a design that really is meant to be very small. And incidentally, I should note, as you're probably aware, that the, I don't know why I don't have the double bed design in there. Oh well. Where?
54.
54. Oh yeah, I must have hidden the slide. Okay. So this is one example of such a design, which I find very interesting. It's somewhat larger than the Hyperion version, 165 megawatts. But basically, you have this reactor core where small pebbles, basically uranium fuel encased in ceramic pellets, continually drop in from the top. And over time, the spent fuel continually falls out the bottom. So this type, you never have to go offline to refuel them. It's continual refueling all the time. But the neat thing about this design, which includes the passive safety feature that makes them intrinsically resistant to having any kind of meltdown, is that the pellets, given their small size and the ceramic casing, never get hot enough to melt down. With a conventional reactor, with the fuel in these long rods, and then you have the bundles of rods, if the rods should break or whatever, and the fuel should pool at the bottom of the reactor, you can get a critical mass and have a huge release of energy when it fissions. But that can't happen here, supposedly. Yes?
You went over rather fast the transition, how we get from dangerous radioactivity from hundreds of thousands of years down to 500 years. Could you explain that again?
Yeah, sure. As you know, the lifetime of a radioactive substance depends on the particular nuclide. So different elements have different lifetimes. The spent fuel is a mixture of all different, a witch's brew of all different nuclei, some of which have short lifetimes, some of which have long lifetimes. And that graph showing how the radiation decays with time is basically the sum of all the different nuclides weighted in proportion to how much of each is present. But if you remove the ones that have the longest lifetime and just store the remainder, then it'll have a much shorter lifetime, the fuel that you. But then what about the other stuff you burn up in a reactor? Because a lot of it is perfectly good fuel for a reactor.
Well, why do we do that today with the conventional?
Well, we decided some time ago not to go that route. What's that?
President Carter.
President Carter made a decision that that was not a good thing to do. And it was partly a fear of nuclear proliferation. What other reasons? I don't know.
The plutonium problem?
The plutonium issue was an issue also, but we chose not to go down that route. Some countries have. Yes?
What do you think about thorium reactors? Because I've read that they are...
I'm very keen on thorium reactors, yes. I think thorium has a lot of advantages. It's much more abundant than uranium. And many of the problems with uranium reactors.
I read that it burns, they use the reactors at much lower temperatures, so there's much less likely to have an explosion. Also, you can run it with a particle beam, and you can turn off the particle beam.
I think there's a lot of advantages of thorium reactors. Let's see. Yes, sir.
What do you think about the floating nuclear power plants? I mean, down there in the Newport News, they built the nuclear aircraft carriers up into an electric boat and connected to the nuclear submarines. Can the same technology be used for nuclear?
Yeah, I meant to say, as you know, that small modular reactors actually have been around for a long time in the U.S. Navy. without, as far as I know, a major incident. So it's not like we're talking about a whole new technology. They've been around a long time, but they haven't been used in the commercial realm. Yes?
Yeah, you mentioned several things in the beginning of the talk about global warming. I believe global warming is not our problem, it's global heating. As long as we have ice in the polar regions and water vapor, the Earth will be at the triple point of water in terms of partial pressure and everything. And added heat will only tend to melt the ice. So the result is that we have to watch the heat flow and the energy flow, and added heat, the global heating has the problem of creating violent storms.
I'm not sure I understand the difference between global heating and global warming.
Global warming says the temperature's going up.
Right.
Global heating says there's more energy coming in than going out. That's different. And it doesn't mean that the temperature's going to go up, it means that there's going to be a lot of heat flow. And that's what we have to watch and keep.
Well, certainly having the polar ice melt and having the Greenland ice sheets melt is probably not a good thing.
If they're gone, then the temperature will not be bounded.
Yeah, so, but whether it is global warming or global heat, both of them would be a matter of concern.
Yeah, but the ice caps tend to mute the global warming, but the global
Ice
heating
caps
is still
tend
there.
The presence of the ice caps tend to
The
melt.
presence of the
Yeah,
ice cap,
sure,
because
sure.
it's a heat sink.
And they also, well, right. You see somebody who hasn't, sorry.
About 2 more questions.
2 more questions. Anybody who hasn't yet asked a question? That gentleman.
Hey, going back to this utopian automobile you displayed there.
Right. I wasn't advocating for it, remember.
Pardon? Yeah, it's utopian. Is there such a thing as a compact nuclear reactor? I don't think there's this. Yeah, you have a nuclear submarine where you have the ocean for cooling, but is there such a thing as a compact nuclear
How
reactor?
compact is compact?
Pardon?
How compact?
Well, 20 tons, so you don't have to tow the thing on with a trailer if you've got a compact, if you've got a nuclear automobile.
Well, hot tub size is pretty compact. You want something smaller than that?
Can you can't take nuclear power and put it in your pocket and carry it around.
No. You wouldn't want to.
Well, I was just wondering, we're talking about this automobile again.
Yeah, I mean, there is this matter of critical mass with a reactor.